Okay, so we're building up still to a way that we can tell, we can definitively tell whether a sequence is graphical or not. And so, well, I guess there's not that much more build up. We're there. It's the next theorem. So here's the theorem. So suppose we have a sequence of numbers called S, and that this is sort of in like the standard form for a degree sequence, like it's in non-increasing order, and assume that the maximum degree is at least 1. If the degrees are all 0, then it's very easy. If all of the numbers are 0, then of course the sequence is graphical, because you can just draw a graph with a bunch of vertices and no edges, and everything will have degree 0. Otherwise, the maximum degree is at least 1, and will be in this situation. And the way you can tell whether such a thing is graphical or not is the following. S is graphical if and only if the following sequence is graphical. It looks a little funny, so let me break it down. This sequence, first of all, my blue pen is not so great. First of all, this is a shorter sequence than the one we started with. S is a sequence of length n. It starts at D1, goes to Dn. This one, it's a sequence of length n minus 1. The first is D2 minus 1, and then D3 minus 1, and then, so basically D1 kind of disappeared, and if you count these, there's, only n minus 1 of them. Also, what's the deal with these minus 1s? Some of these have a 1 subtracted. Starting at D2, we subtracted 1, and then going all the way up to D sub delta plus 1. But then I don't subtract 1 after that. The next degree is just whatever it was before. It's D sub delta plus 2, D sub delta plus 3, all the way up to Dn. Right, so just roughly speaking, I kind of, this theorem is supposed to evoke an image in our brains, and I drew that image in the corner. Theorem 1.10 in the previous video was about graphs with this special property that the neighbors of V1 are precisely in this consecutive block starting at V2. So it's the neighbors of V1 are V2, V3, V4, all the way up to whatever, V sub delta plus 1, so that there's a total of delta of them. And then maybe there's other vertices in the graph, so but those are not neighbors of V1. The neighbors of V1 are all in a consecutive block starting at V2. And this clearly has something to do with this. More specifically, if I were to take this picture and remove the vertex V1, and by the way, when we talk about removing a vertex from a graph in graph theory, you also remove all the edges touching that vertex. So if I'm removing V1, then I'm going to have n minus 1 vertices, just like how this sequence has n minus 1 terms in the sequence. Also, what effect would it have on the degrees if I removed V1? First of all, V1's just gone, so there's no entry for V1 in the sequence, and that's why the sequence became shorter. But second of all, V2 has lost a neighbor. V2 used to be a neighbor of V1, and that edge is now gone because when I remove V1, I remove all the edges touching V1. So V2 now has this degree instead of D2. V3 now has this degree, all the way up to V sub delta plus 1, which also has 1 subtracted from its degree. The other vertices are unaffected if I remove V1. So what I just talked about isn't the formal proof. It's pretty much hinting at the formal proof. But it's definitely, I think it's helpful to think about and just to try to understand what this theorem is saying and why it's saying that. And ultimately, this is the theorem that we're going to use to determine whether a sequence is graphical. And I'll show you in practice how to actually do that in a bit after we prove it. So first, let's prove it. This is an if and only if statement. Basically, it just says that as long as we understand what S is, that it's this degree sequence, and we understand what S sub 1 is, it's this other degree sequence. The theorem is really just saying that S is graphical if and only if S1 is graphical. So there's two directions to prove. I'm going to prove the forward direction first, meaning that I'm going to show that if S is graphical, then S1 is graphical. So suppose S is graphical. Then theorem 110 implies that there's a special graph G, right? That theorem 1.10 tells us that for any graphical sequence, you can take a graph H with that degree sequence, and by a sequence of two switches, you can obtain a special graph with that degree sequence. And of course, specialness, once again, just means the neighbors of V1 are in a consecutive block starting at V2. So since S is graphical, that theorem tells us there's a special graph with that degree sequence. And this is just restating what the specialness means. Now, by deleting V, this should say V1 from G. And by the way, we call that G minus V1 in graph theory. If we're removing a vertex, we call the new graph G minus V1. We obtain a graph with degree sequence S1. And this part of the proof basically is what I was saying up in this picture. It's that if I start with this, and this is a special graph because the neighborhood of V1 is these. If I just remove V1, then I'll get this degree sequence, as we discussed, because these vertices now have one less of a degree, and that's why these minus ones are there, and then these vertices don't have a minus one. So yeah, that's the forward direction. If S is graphical, then I can come up with a graph that looks like this and has degree sequence S, and then from that graph I can just remove V1, and that shows that S1 is graphical. Conversely, we have to show the other direction. So I'm going to show that if S1 is graphical, then S is graphical. So suppose S1 is graphical. That means that there's a graph with that degree sequence. So let G1 have that degree sequence. And sorry, I wrote sideways because I couldn't fit it because this is an afterthought. Let's assume G1 has vertex set V2 through Vn. It's a bit awkward. Usually if I just come up with a graph and I want to name the vertices, of course I would start with V1. But the idea for this proof is I'm going to start it's like doing the previous part backwards. So for the previous part, I came up with a graph and then I removed V1. For this part of the proof, I'm going to come up with this graph and then I'm going to put in a new vertex that I'm going to call V1. So I don't want to have a vertex that's already called V1. I'm going to put in a vertex to this and call that V1. That's why I'm naming the vertices of G1 will start at V2. Once again, suppose S1 is graphical, and so there's some graph G1 that has that degree sequence and this set of vertices. Then by adding a new vertex V1, and I'm going to make it adjacent to V2 through V delta plus 1, and everything about this is right. The degree of V1 is supposed to be delta, and if you count how many of these are, there are delta of them, because we're starting at 2 and going, man, this blue pen is just a nightmare. Oops. So there's delta of these. And so the degree of V1 will be delta, because those are the neighbors. And also, each of these degrees, like the degree of V2 in the graph we started with, was D2 minus 1, right? Because G1 has degree sequence S1, and so the degree of V2 is actually this. But then when I make V1 adjacent to V2, that bumps it back up by 1. And so now it's the degree of V2 in G will just be D2, as it's supposed to be. And so everything's right. We obtain a new graph with a degree sequence S. Let me put a proof box at the end of that. Okay. So that got a bit technical and abstract, but it's not that hard to use. Now that the painful proof part is over, this is not that hard to use. So, for example, here's a sequence, and actually this is... Since I have not been very creative throughout this lecture, you'll notice that in a previous example, in the last half of this lecture, I did a graph that has this degree sequence. It was 4, 3, 2, 2, 2, 1. And so we're talking about that degree sequence. And so we already know that it is graphical, because we already saw that this graph has that degree sequence, for example. But suppose we didn't know. Suppose somebody just gives you this degree sequence and says, tell me whether it's graphical or not. Then what you do, so this is in order. It's in non-increasing order. I take the biggest number, and then I take the next that many. So this is a 4, so I'm going to take the next 4. And now I'm going to make a new list where this is just gone. The 4 is just gone. There's nothing there. And then these that I underlined all have a 1 subtracted. So this 3 is a 2, 2 is a 1, 1, 1, and this last 1 is unaffected. So this is graphical if and only if this is graphical. And the idea behind this is each time we do this, it should be easier to tell whether the new thing is graphical. The truth is, well, in my opinion, it's not that hard to see that this is graphical. But then I'm a graph theorist, so maybe it's not that easy in general. Let's say we can't tell whether this is graphical still. I can just do it again. First of all, you have to make sure that these are in order. It's sometimes when you do this operation, your new numbers will not be in order anymore, and if that's the case, you can just put them in order. But they are in order, so I take the biggest one, which should be the first one, because they're in order, of course, and then I take the next that many. So that this is a 2, so I take the next 2. And now I'm going to make a new sequence. This 2 is just gone, and these that I underlined each have a 1 subtracted. So it's 0, 0, 1, 1. Now, this is easy enough to tell that this is graphical. Here's a graph with that degree sequence. It would have 4 vertices, because this has length 4. I'm going to have 2 vertices of degree 1 and 2 vertices of degree 0. So this one is indeed graphical because I drew a graph with that degree sequence. And so that means they're all graphical. Now, suppose we weren't satisfied with that. Because what am I saying here? I'm telling you that this sequence is graphical. That just tells you that there exists some graph somewhere that has that degree sequence. But I'd like to know what it is. Or what is an example of a graph with that degree sequence. It's possible to use this and tell. It's possible to start with this graph and then go backwards. So how do we do this? Basically, to go backwards, the idea is the neighbors of V1, so like, what I'm going to do is I'm going to come up with the special graph. And in the special graph, the neighbors of the first vertex consist of a consecutive block of vertices starting at the next vertex and going onward until you're done. So the idea was if this was graphical, we were going to make this 2 adjacent to these 2 1s, which became these 2 zeros. So here's what I'm going to do. I'm going to start by drawing the same graph I had over there. I'm going to put in a new vertex. This vertex is going to be the degree 2 vertex. And what are its 2 neighbors going to be? Its 2 neighbors are going to be these, which became the zeros. In other words, it's these. So here's a graph with degree sequence 2, 1, 1, 1, 1. Finally, I can do it again. I can draw the graph that I had. And now I'm going to put in a new vertex. The new vertex is going to have degree 4. It's going to be adjacent to 4 of these vertices, but I have to intelligently choose which 4. So maybe I'll draw the new vertex here. Well, the 4 should be adjacent to these 4, which is like the first 4 of these. Like this 3 became this 2, this 2 became this 1, this 2 became this 1. So I'm going to take, let's see here, do I have I have a better blue pen. I'm going to take these 4. So a 2, a 1, a 1, and a 1. And those are going to be the neighbors of this. So here's a 2, and then I have to pick 3 of the vertices of degree 1. And it doesn't really matter too much what I do. So maybe the neighbors of this will be definitely this one because this is the 2, and then 3 of these other ones. I have 4 vertices of degree 1, and I just have to pick 3 of them. So this one, and then why don't we say 1, 2, 3. And this graph has a degree sequence. Let's see. This one is the degree 4, of course. This one is the degree 3. Then I should have 3 vertices of degree 2. There's this one, and this one. And then there's a vertex of degree 1. Okay. So why don't we try to do that one more time with a longer degree sequence. So we have this degree sequence, and the question is, is it graphical? And if it is, draw a graph with that degree sequence. So let me try to be organized about this. 7, 4, 3, 3, 2, 2, 2, 1, 1, 1. And we know how we do this. So these are in order. I'm going to look at the first number and underline the next that many. So 1, 2, 3, 4, 5, 6, 7. So the next thing I'm going to write, and so these underlines ones all get 1 subtracted. So 3, 2, 2, 1, 1, 1, 0, 1, 1. And like I was talking about, sometimes after you do this, they're no longer in order. So let me go ahead and put them in order. I've got 5 ones. Yeah, it looks shorter, but that's because I wrote them closer together. Yeah, it has 2 2s, 5 1s. Yeah. And now I'm going to do it again. So I take the biggest number, should be the first one because they are in order, and I underline the next that many, so the next 3. And now I'm going to write a new sequence. So these get a 1 subtracted, so 1, 1, 0, and then 1, 1, 1, 1, 0. Let me put this in order. So yeah, I've got 6 ones. Okay. I can tell you what we could do. I could keep going. I can keep doing this until I'm like basically down to a sequence of only zeros. I don't want to do that because like the next, this gets really boring after a while. The next step is I see a 1, so I would underline the next that many, and then I would subtract a 1 from this, so this would now be a 0, and then I would move that to the end and keep going. And there would be several steps that are all just killing off all of these 1s. I've got 6 1s to kill off that way. But I don't have to do this all the way down until I get a sequence of all zeros. I can look at this, and with what I'm about to tell you, you can all look at this and tell that it is graphical. A sequence that only consists of 1s and 0s is very easy to tell whether it's graphical. To have vertices of degree 1, basically, they just have to be you have to have like pairs of vertices that are adjacent to each other, and they're not adjacent to anything else. So what I'm going to do is over to the right, I'm going to try to draw graphs that have this degree sequence. So once again, where are we? I've looked at this, and I'm telling you that this is graphical, and I'm going to explain how I know that. And then I'm going to draw a graph with this degree sequence, and then I'm going to work my way backwards as we did last time. So how can I tell that this is graphical? Well, the easy answer is that it's all 1s and 0s, and the number of 1s is even. That's all it takes. So how can I draw this? I've got 6 1s. There's 6 vertices of degree 1. And then I've got 2 zeros. So there's 2 vertices of degree 0. See how easy that was? So basically, if you have any even number of 1s, you can do this. Like 6 1s just turns into 3 of these. And then zeros are even easier. You just draw vertices floating off in space, not doing anything. Okay, now from here, let's work our way backwards. So I'm going to draw the same thing, but I left myself a little room to the left. And yeah, oh. Smudgy. This is not an edge. Maybe, yeah, it doesn't look that bad. This is not an edge, though. That was just a smudge. Okay, so what do we do? I drew the last graph. Now what I have to do is I have to add a vertex, and this vertex of degree 3 was supposed to be adjacent to the next 3, which basically became these 3. Right? I subtracted 1 from each one of these, and that's how I got 1, 1, 0. So the vertex of degree 3 should be adjacent to, referring to these, a 1, and a 0. So here's a 1. Here's another 1. I have a lot of choices here. But maybe I'll do this one, and then a 0. And this graph now has this degree sequence. There's a vertex of degree 3, a vertex of degree 2, another vertex of degree 2, a 1, a 1, a 1, a 1, another 1, and a 0. Finally, let me first of all start by drawing the previous one. So I just drew what I had so far. And now I'm going to draw one new vertex with certain neighbors. This 7 is adjacent to these 7. These 7 became these. So this vertex is going to be adjacent to some stuff over here. In particular, it's going to be adjacent to the vertex of degree 3, 2 vertices of degree 2, 3 vertices of degree 1, and then a vertex of degree 0. Let me, in order to help myself here, let me put, well, I'm just going to write a little number, just whatever its current degree is. So this one's current degree is 3, 2, 1, 2, 1, 1, 1. Just because otherwise I'm afraid I'll get confused. So these numbers that I wrote, they're not the names of the vertices, they're the degrees of the vertices. And I'm doing this because I'm about to draw more edges, and when I draw more edges, the degrees are going to change. But I just want to have this written there so I remember what the original degree was before I started drawing this. And okay, so once again, This vertex is going to be adjacent to 7 other vertices. In particular, it's going to be adjacent to a 3, a 2, a 2. So a 3, I guess it has to be adjacent to both of the 2's. So 3, 2, 2. And I need to pick 3 1's. So maybe, in the interest of drawing a picture that isn't terrible to look at, I'll pick this one, and this one. So that's 3 1's and a 0. And maybe the best way to do that is just go around like this. And yeah, the picture got kind of hairy there, didn't it? But if we check the new degrees, the new degree sequence is this. We've got our vertex of degree 7. This vertex that had degree 3 now has degree 4. So this counts as the 4 now. This had 2, but now it's 3. This is now 3. This is now 2. This is now 2. This is now 2. This 0 is now a 1. And this 1 is still a 1, and this 1 is still a 1. And that's the last 2 1's. So we did it.